Alright, so Unit 8, we are going to talk about the periodic table a lot and how there are different patterns and things you can find on the periodic table. Now, it all starts talk with valence orbitals, valence shells, and valence electrons. We just talked about that in Unit 7. Valence just means the outermost, so the outermost shell. Valence electrons are the electrons in the outermost shell. So, before we move on to the actual stuff, let's review real quick, just because we talked about it. I want you guys to look at each of these elements, and I want you guys to write two things for each element. How many total electrons do they have, and how many valence electrons do they have? So take about 2 minutes, just jot them down on your paper. So how many total electrons does potassium have? How many valence does it have? And just do it for all 6 of these. We'll go over it, and then we'll move on to the new stuff. So that means that it's going to have 2 total, because the atomic number is 2, and it is box number 2 in its row, so it's going to have 2 valence electrons. Okay, chlorine, same thing. Atomic number is 17, so chlorine is going to have 17 total. It is box number 1, 2, 3, 4, 5, 6, 7, so it'll have 7 valence electrons. Okay. All right, now we're going to get into the ions. So we're going to take a look at K+. Now, if you take a look at K+, we got to think about K first. K+, the plus sign means you lose 1 electron, right? And so if it had a total of 19, now it goes to 18 total. And in terms of the valence, we talked about this already, but potassium, it has 4 shells. It has 1 electron in the 4th shell, so if you lose that electron, that 4th shell disappears. And so K plus is not going to have 1 valence electron. It's going to have whatever the noble gas before it had. So Ar. Ar has 8, so it's going to have 8 valence electrons because that 3rd shell became its new valence shell. Okay. Next one is S2 minus. S is right over here. Typically sulfur has 16, but we got to add 2. So that means we have a total of 18. And it normally has 6 valence electrons, but it goes to 7, 8. So it has 8 valence electrons. And then the last one, Cl minus. Cl typically has 17, but if it's minus 1, you add an electron, so it's 18 total. And then, since it had 7 valence electrons, it becomes 8 valence electrons. And if you guys take a look, all 3 of these look exactly the same, right? It's because all of them are trying to get to their noble gas. So sulfur wants to become S2 minus so that it can fill up its shells and become like Ar, which is a noble gas. Cl gains an electron to become like Ar. And K wants to lose an electron to become like Ar. Okay, so that's kind of the reason why we have the most common ions that we do. Everybody pretty much wants to be a noble gas because a complete shell is a stable shell. They want to have stable energy levels. All right, let's move on. So we're going to talk a little bit about something called effective nuclear charge. And the symbol for this is called Zeff. So, oh, what happened there? Z and then effective, so F, Z-E-F-F, Zeff. And basically what this describes is it describes the electrical attraction that an electron feels to the atom. So basically, how tightly does the atom hold on to a specific electron? Okay. And it's very simple. It's the electronic things that are in the atom. So the first thing that matters is something called or something that you already know about. It's the number of protons that it has. We use the symbol Z. Okay, so the first thing that matters is the number of protons. Remember, protons are positive, electrons are negative, so they are attracted to each other, right? So basically what the protons are trying to do is they're trying to pull the electrons in towards the atom. But we also remember that electrons are all negative, so they push each other away. So as electrons try to get closer to the nucleus, these other electrons are also trying to get close, and they start pushing each other away. Okay, so it's like the protons are like this really attractive girl, and there are all these thirsty guys trying to get closer to her, but as they get closer, they start pushing each other away, right? And that balancing act is what we call effective nuclear charge. Okay? Now, calculating the effective nuclear charge is very easy. It's going to be the number of protons minus the number of inner electrons. Okay, so this is the formula. It's the number of protons minus the number of inner electrons. I'll talk about why it's inner, not total number. Okay, but a quick thing about this calculation is that the higher the Zeff number, the more tightly the electrons are held. Okay, so if an electron has a super high Zeff number, it means that it's held extremely tightly by the atom. It's really hard to remove or ionize.
So iron has like a tighter Zeff number than potassium, which is why I didn't do the thing.
Yes, it does. Okay, so let's talk about how to calculate this. So to do this, we're going to look at phosphorus right here. This is our diagram. And we're going to look at the Zeff for phosphorus. Now, phosphorus is element number 15, right? So it has 15 protons. So that's P right here. So this is number of protons. Minus the inner electrons. If you look, the valence electron of potassium is the third shell, right? So all we got to do is count up the electrons in the inside shells. There are 8 in the second shell and 2 in the first shell. So the number of inner shell electrons is 10. So 15 minus 10, the Zeff is plus 5. So the electrons in the outside shell, they have a Zeff of positive 5. Yes.
So the outer shell is just like
Yeah, valence is the outside shell. Yeah, basically anything that's not the outside shell. Correct. Okay, so pretty easy calculation. It's just counting and then subtracting. All right, so I want you guys to real quick, I want you to calculate the Zeff for carbon and sodium's valence electrons. Carbon and sodium. Give you guys about 2 minutes to do that, and then we'll go over it. All right, so to calculate Zeff, we got to do protons minus inner shell electrons, basically the non-valence electrons. So it's protons minus inner electrons. Okay, so we're going to look at the protons for carbon first. So let's do carbon. Carbon has 6 protons, right, because it's number 6. And then we need to figure out first how many valence electrons does it have. Well, if you look, it has 4 valence electrons, right? Which means we have 2 non-valence or inner electrons. So it'll be minus 2. 6 minus 2 is plus 4. Okay, so carbon, its valence electrons have a Zeff value of plus 4. So far, so good? Okay. Let's take a look at sodium. Sodium has 11 protons, and it has 1 valence electron. That means it has 10 inner shell electrons. So that means the Zeff value is plus 1. So this actually goes along very well with what we know about these elements. Okay, we know that sodium, its most common ion, the ion that it wants to become is Na+, right? That means it wants to lose 1 electron. However, carbon's most common ion is 4-. That means it wants to gain 4 electrons. So that means that if sodium wants to lose an electron, it's not holding that electron very tightly, right? Because it wants to get rid of it. And so if you look, the Zeff value is very low because it wants to get rid of that electron. Whereas carbon, it wants to gain electrons. So if you want to get more electrons, you're probably going to be holding on to the ones you have pretty tightly already. And that's why it has a higher Zeff value than something that wants to lose the electron. So Zeff just basically means it wants to hold the electrons tighter. The bigger the number, the more it wants to hold on to those electrons. All right, now there is one other thing that we need to know about Zeff. Okay, so we've been talking about the Zeff of valence electrons. Okay, so up until this point, we have been looking at Zeff, okay, for valence electrons. Okay, we've been looking only at the electrons that are not the valence shell. But it is actually possible for people, or we've seen questions on the AP test where they ask you not for the Zeff of valence electrons, it asks you for the Zeff of the electrons in an inside shell. So for example, it'll ask you for the Zeff of an electron in like the second shell. So we're gonna do a problem like that for phosphorus. Okay? But the calculation is exactly the same. We just need to know what we are looking at. So if you take a look at phosphorus, if we're calculating the Zeff for anything that has to do with phosphorus, we take the protons first. It has 15 protons. But now we're looking at an electron in the second shell, not the outside shell. So we're going to subtract the value, but we're going to look at the electrons only underneath the second shell. So there's only one shell. And how many electrons are in that inside shell? 2. So we're going to subtract 2. So that means that inside the second shell, the Zeff of the electrons is positive 13, whereas the ones in the outside shell, it's positive 5. And that makes a lot of sense, because the closer the electrons are to the nucleus, the more tightly they're held. So on the outside, it's plus 5. Second shell, it's plus 13. And if you go to the first shell, this is going to be plus 15, because there's no inner electrons. It's just the protons attracting it. Okay, so as you go deeper into the atom, the higher the Zeff values, because the electrons are held tighter and tighter as you get closer.
So why is it